طيب يعني عزيز بابتي درسي أمرومان بريتيلا chapter 4 وأتا chapter 4 بناونشاني thermal properties of solids. So today's subject is chapter 4 in the solid state physics titled thermal properties of solids. Heat capacity. The heat capacity C of a system is the ratio of the heat added to the system or withdrawn from the system to the resultant change in the temperature. C equal to Q divided by T or dQ by dt joule per degree. This definition is only valid in the absence of phase transitions. Usually C, the heat capacity, is given as a specific heat capacity C per gram per or per mole. Heat capacity is the measure of how much energy it takes to raise the temperature of a unit mass of an object at a certain amount. Two heat capacities, constant volume heat capacity CV and constant pressure heat capacity CP. For a gas, CP always greater than CV. For a solid, CP approximately equal to CV, very near to each other. Thus, two distinct heat capacities can be defined. CV equal to dQ by dt whole constant, heat capacity at constant volume, CP equal to dQ by dt whole constant at constant P, heat capacity at constant pressure. Heat capacity is a measure of the ability of the material to absorb thermal energy. Thermal energy equal to kinetic energy of atomic motions plus potential energy of distortion of interatomic bonds. The higher is the temperature T, the larger is the mean atomic velocity and the amplitude of atomic vibration per larger thermal energy. The coupling of atomic vibration of adjacent atoms results in waves of atomic displacement. Each wave is characterized by its wavelength and frequency. For a wave of a given frequency nu, there is the smallest quantum of vibrational energy, h nu, called phonon. Thus, the thermal energy is the energy of all phonons, or all vibrational waves present in the crystal at a given temperature. Scattering of electrons, or phonons, is one of the mechanisms responsible for electrical resistivity. Temperature dependence of heat capacity. The constant value of the heat capacity of many solids is called Dulong-Pettit law. In 1819, Dulong and Pettit found experimentally that for many solids at room temperature, CV approximately equal to 3R, which is about 25 joule per Kelvin per mole. This graph shows the variation of heat capacity at constant volume in units joule per kilo per Kelvin per mole as a function of the ratio of temperature to divide temperature. It can be seen that at the beginning, the heat capacity increases until it reaches about a fixed value, which is approximately equal to 3R or 25 joule per Kelvin per kilomole and will remain constant. Temperature dependence of heat capacity. The low temperature behavior can be explained by quantum theory. The first explanation was proposed by Einstein in 1906. He considered a solid as an ensemble of independent quantum harmonic oscillators vibrating at a frequency nu. Debye advanced the theory by treating the quantum oscillator as a collective mode in the solids called phonons, and he showed that CV is near to a T cube at T approaches 0 Kelvin. Here, the heat capacity at constant volume, a graph shows a various temperature in Kelvin for various crystal structure elements, for diamond, for silicon, for Cu, and for lead Pb. It can be seen that all the graphs is almost similar. Heat capacity of metals, electronic contribution. In addition to atomic vibration, that's to say phonons, thermal excitation of electrons can also make contribution to heat capacity. To contribute to specific heat, the valence electrons would have to receive energy from the thermal energy, which is about kT. Thus, only a small fraction of electrons which are within kT of the Fermi level makes a contribution to the heat capacity. The electron contribution to CV is proportional to temperature. So CV electrons equal to gamma T and become significant for metals only. At very low temperature, remember that contribution of phonon CV is about 80 cube at T approaches 0 Kelvin. And here in this equation, EL means electronic or electron. Variation of CV with T cube, CV equal to 8T by theta D all cube. These two graphs shows the law of Dulong at Petit. Here, CV, here at low temperature, C behaves like much. Depart from the pi model, there is difference, but similarity, but a very small difference between the two graphs. This is for silicon specific heat, this one for copper specific heat. The variation of CV with temperature cubed. And the equation is given here. 0 point energy. The lowest possible energy that a system has at ground state is first proposed by Albert Einstein and Otto Stern in 1913 was termed as 0 point energy. E naught equal to half h nu, where h is Planck constant and nu frequency. Phonon, what's phonon? Phonon in condensed matter physics, a unit of vibrational energy that arises from oscillating atoms within a crystal. Any solid crystal, such as sodium chloride, consists of atom bound into a specific repeating three-dimensional spatial pattern called a lattice. So a quantum of crystal lattice vibration is called a photon. So a quantum of crystal lattice vibration is called a phonon. Phonons are particles of sound, elastic waves, because the atoms behave as if they are connected by tiny springs. Their own thermal energy make the lattice vibrate. This generates mechanical waves that carry heat and sound through the material. A packet of these waves can travel throughout the crystal with a definite energy. Types of phonons. So in quantum mechanical term, the waves can be treated as a particle called a phonon. A phonon is a defined and discrete unit or quantum of vibrational mechanical energy, just as a photon is a quantum of electromagnetic or light energy. There are two general types of phonons. Acoustic phonons, which have zero frequency at K equal to Kelvin, K equal to 0, and are associated with propagation of sound waves in a solid. Optical phonon, which have non-zero frequency at K equal to 0 and can couple to light. Thermal properties. The most important thermal properties of materials are thermal conductivity, thermal expansion, and the thermal expansion are of three types of thermal expansion. A, linear thermal expansion, B, area thermal expansion, and C, volume thermal expansion. Thermal conductivity kappa. Thermal conductivity kappa refers how heat can move through a material. Metals have high thermal conductivity, means high pass through it easily. Wood is insulator for heat transfer and has low thermal conductivity. K is very low for air also. The rate at which heat is transferred is given by dq by dt equal to kappa A, T2 minus T1 divided by L, or H equal to Ka divided by L multiplied by T2 minus T1. Here, A is area of a side wall, L thickness of the wall as shown in the figure, K thermal conductivity of the metal, T2 minus T1 temperature difference, and here H is equal to dq over dt, which is equal to power in unit of joule per second, and is called watt. This figure shows the three types of thermal expansion. Linear expansion, we have a rod, and aerial expansion, we have an area, and volume expansion, we have a bottle or a cube. Here, in linear expansion, delta L divided by L naught equal to alpha delta T, while in area expansion, delta I divided by A naught equal to 2 alpha delta T, and in volume expansion, delta V by V naught equal to 3 alpha delta T. Here, alpha is coefficient of linear expansion, and delta T is the temperature difference. Thank you very much for your listening, and I hope it was a useful lecture for you and wish you a good success. Best regards.